Vector calculus is another important component of mathematics. Actually, when we discuss about vectors, we'll have vector algebra followed by the calculus of vectors. Calculus deals with differentiation, integration, and of course, to discuss differentiation and integration, we also require the concepts of limit and continuity. Vector calculus finds applications in many fields, in particular in electromagnetic field theory. Electricity and magnetic field are closely related to one another. From magnetic field, you can have derived electric field, or from electric field, you can have derived magnetic field. It plays a vital role in many applications. When we come to vector calculus, since calculus deals with differentiation and integration, let us initially discuss vector differentiation. To discuss vector differentiation, let's consider the basic definition of vector differentiation or derivative of a vector. To define derivative of a vector, we consider what is meant by a vector function. Suppose you consider a particle moving in space. It will be at different positions at different instants of time. So the velocity can be observed to be a function of the time variable. If f bar, a function of t, is used to denote either the position vector or velocity or acceleration of a point moving in space, then you can think of derivative of the function with respect to the time variable. Using the fundamental principles of calculus, we can expect d by dt of f bar of t, that is the derivative of the function, is equal to limit delta t tending to 0, f bar a function of t plus delta t minus f bar t divided by delta t. But we know that vectors always can be expressed in component form. If you have got a vector in a two-dimensional plane, it will have two components. If a vector is considered in space, it will have three components. So if f bar t is denoted as or written as f1 a function of t into I bar plus f2 a function of t into j bar plus f3 a function of t into k bar. That means if f1, f2, f3 are its components, then df bar by dt can as well be written as d by dt of f1 a function of t multiplied by I bar plus d by dt of f2 a function of t multiplied by j bar plus d by dt of f3 a function of t multiplied by k bar. Whatever the general rules for differentiation of scalar functions are known, they will be applicable for vector functions also. In fact, we can notice that d by dt of dot product of two vector functions is equal to derivative of the first function dot second function plus first function dot derivative of the second function. If k is a scalar and f bar is a vector, d by dt of k times f bar is equal to k times df bar by dt. Whatever function of function rule is known to us, or whatever rules are known for derivative of product of functions, those will be applicable for vector functions also. To further our discussion of the calculus of vectors or differentiation, let us understand what is meant by a scalar point function and a vector point function. What do you mean by a scalar point function? Certain scalar quantity, if it is defined over a region of space, then it can be referred to as a scalar point function. For example, you can consider the temperature in the vicinity of a burner where there is a flame. You understand that the temperature will be more nearer to the flame and it will be less as we go away from it. Or if you consider water in which some material is mixed up, if it is changing from position to position, you can think of the density or the concentration of the material as a scalar function of the position. A scalar point function is denoted by phi, a function of xyz, or f, a function of xyz. If a scalar function at all points of a region of space is defined, then we can call it as a scalar field. Examples I have already mentioned: temperature distribution in a medium or in a particular portion of space. For example, in the vicinity, or I can say in the neighborhood of a burner where there is a flame. Another important quantity is the vector point function. For mentioning what is meant by a vector point function, let us think of a particle moving in space. When a particle is moving in space, we know that definitely the path of the particle will be a curve in space. We know that the velocity vector will be tangential to the path of motion. So when the particle is moving, what happens is the velocity vector will be a function of the position and its direction changes at each and every instant. Therefore, it is an example of a vector point function. You can take position vector of a particle, or you can consider the velocity of a particle moving in space. Another example is the gravitational function. All these are examples of vector point functions. A vector point function is usually written as f bar, a function of xyz, or in particular, suppose you consider velocity, you can as well write v bar is equal to v bar, a function of xyz. If a vector function is defined over a region of space, you can as well say that a vector field is defined. Then, when it is written in component form, even if you write f bar is equal to f bar, a function of xyz, still you can write f bar is equal to f1, a function of xyz into I bar, plus f2, a function of xyz into k bar, plus f3, a function of xyz into k bar. Of course, in 3 dimensions that we write like this. If it is in 2 dimensions, then you can write f bar is equal to f1, a function of xy into I bar, plus f2, a function of xy into k bar. Then we shall get introduced to an important vector differential operator. All of us know that if you have got a function of xyz, you can think of differentiation with respect to x, derivative with respect to y, or derivative with respect to z. In this context, we come across the differential operators dou by dou x to denote derivative with respect to x, dou by dou y to denote derivative with respect to y, dou by dou z to denote the derivative with respect to z. All these are scalar differential operators. On the other hand, we come across vector differential operators in this context. The general vector differential operator is denoted by del. It stands for I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z. Let's now get introduced to one important quantity we come across in the calculus of vectors, that is the gradient. What is a gradient? Gradient is obtained by operating the vector differential operator del on a scalar point function. Suppose f is a scalar point function. If you operate del, the vector differential operator on it, the result is known as gradient of f. We write it in abbreviated form as del f, or the word grad followed by the function f. How do you define? Grad f is defined as I bar dou f by dou x plus j bar dou f by dou y plus k bar dou f by dou z. Is it or does it have any significance? Yes, it is a very important quantity. What does gradient of f gives? Initially, we observe that it is a vector quantity. So, in which direction it will be acting? What is its magnitude? What is the significance? Grad f will be a vector and it will be acting in the direction normal to the surface f is equal to constant. If you consider any particular point, that means any point on the surface, at that particular point if you determine grad f, then grad f will be representing the normal vector to the surface at that particular point. As far as the magnitude is concerned, grad f gives maximum rate of change of the function f. Grad f gives maximum rate of change of the function. So, this is the significance of gradient. It will be acting in the normal to the surface. Its magnitude gives maximum rate of change of the function.